Okay, I think we're going to start. Thank you everybody for coming. Okay, so today we have two speakers that come from very far away, from the Institute of Material Science. And you saw maybe the colloquium talk of Esther Arnstadt a few weeks ago. She went over many different topics, and now Antoine and Wachian, they're going to show you some more details about the study they did in the lab. It's mainly playing around with droplets and ending up with different tunable materials. And before we begin, I would like to announce also that we just put all the videos of the seminar on a YouTube channel dedicated. Yeah, and you can find the list of the links on the Flex Lab page. So I'm gonna send everybody the link as well, so you can find back the videos in case you're gonna come to one mega seminar. You can find it back and replay it whenever you want. So first speaker is Antoine Vian, and he's gonna talk to us about double emulsion as a template for encapsulation. Thank you.
Thank you very much for the nice introduction. Thank you for giving me the opportunity to come here and talk a bit about what we do in the lab. So yes, I'm going to talk to you about drops, a generation of drop, and more specifically a kind of drop which are called double emulsions. We use microfluidics to produce them, and we want to use them afterwards as template for encapsulation. So first, I need to show you what are double emulsion drops, and more specifically water, oil, water double emulsion, which we are interested in. It's composed of an aqueous core surrounded by an oil phase, and all of this is in aqueous continuous phase. So it's a drop in another drop, and it has a certain shell thickness here, as you can see. We produce them through the microfluidic device. So this is a device we use. Here you put the water flow, the inner core, and on the side you have a co-flow of oil that is going to be pinched at this level by another water flow. And this way you can form water in oil double emulsions, which have similar size, and they also have similar shell thickness. What's cool is that you can tune the oil flow, so you can tune the shell thickness as well. And that's what's interesting for us. At the end, you obtain double emulsion, we have same shell thickness, same size. Okay, so to go back, I want to say that those double emulsion are interesting because they have a high encapsulation efficiency. There, you can use them, for example, for high throughput screening. They are used in biology. But one must be careful about what you have inside the core. You don't want it to leak out, so you have to be careful that you don't have leakage. And that's a big problem, for example, for biologists. They don't want, if they put the bacteria in, that it gets out and go to another drop. For those double emulsion, the production method that we use, we can only go to micron size shell thickness, we cannot go lower. And that can be a problem in terms of stability of the double emulsion, because it's a drop which is inside another drop, so it can move and maybe break it. So that's why we turn to another kind of double emulsion, which are called thin shell double emulsion. So in this talk, when I'm going to talk about thin shell, I talk about double emulsion, which have a shell thickness of less than 1 micron. They have been shown to be stable over several days, but we tested that ourselves, the stability, by having double emulsion, which have a shell thickness of around 8 micron on the left, and double emulsion, which have a thin shell of around 330 nanometer on the right. And we added a salt solution to destabilize the drop, basically to break them. But what we saw is, for the double emulsions, with the 8 micron shell thickness, they tend to aggregate together and form those kind of multi-core structure they merge together the outer shell and form this stuff. Whereas for the thin shell, they shrink because you have a lot of osmotic pressure, of course, but they seem to remain stable. So that was an interesting feature for those thin shell drops. But if you reduce the shell thickness, you might wonder, like, maybe I increase the leakage. And this is also what we tested. Sorry. Here is 13.4 micron shell thickness, and here is 320 nanometer shell thickness. As you can see, after 15 hours, after 15 hours, like the whole the whole fluorescein that was put inside the double emulsion leaked, whereas for the thin shell we still have some fluorescence. I want to show you, we did the mix in the same image of thin shell and double emulsion, and you'll see how it goes. So all the 13.4 micron shell thickness, they leak faster, whereas the thin shell, they remain with the fluorescence inside. You can measure the intensity as a function of the time. So for different shell thickness, for example, here at 13.4, everything is leaked out in about 200 minutes. For the thin shell in green here, you lose 20% of the initial intensity after 15 hours. So this is from this curve and different experiments, you can retrieve a characteristic time that we can plot as a version of the shell thickness. What's interesting to see in this plot is that if you have a shell thickness between 4 and 13.4 micron, you have a characteristic time which is about 100 to 200 minutes, whereas for the thin shell, it's about 5,000 minutes. So it's drastically, the thin shell seems to leak drastically slower. We have different hypotheses, and this is something we're working on with Gianluca, another member in our lab. We made a different experiment to prove that. But basically here is the water inside the double emulsion, here is the membrane with the oil, and here is the outside. What we think is that those little stars here, they're fluorescent dye, and they get transported via a tiny emulsion in the oil, which are about hundreds of nanometer that we measure with TLS. And that's interesting because our thin shell double emulsion are in the range of within hundreds of nanometer. So we think we might be able to avoid the formation of those tiny emulsions, and that's why we have less leakage. So this is hypothesis again. But I want to get the message that those thin shell are quite interesting in terms of stability and leakage. But how can we form them? I didn't tell you yet. So one technique that has been used to form them from double emulsion template is by forming the double emulsion, but inside the oil of the double emulsion you put a volatile solvent. And as the oil evaporates, the equilibrium is shifted and oil is going to leave the double emulsion. What you're going to end up with is with the double emulsion with little to no oil residue. So this is an interesting technique to produce ultra thin shell, but you can only use volatile solvent. And if you want to use it for biological application, for example cells or bacteria, it can be a bit problematic. So we thought maybe we can kind of force the oil to go out. And that's why we went with this system. So it's just a channel with a construction. And the double emulsion arrived in the channel. It's already compressed on one direction. And it enters the construction. And what we could see is that there is a pinching off of the oil. And what you can obtain at the end is a double emulsion with a thin shell and the oil drop. So we tested that for different flow rate, different speed, and this is what we obtained. Here is the shell thickness that you obtain after the double emulsion has been processed through the construction, and here is the speed in the channel. here in this we have three main behavior. First, for speed lower than 4 centimeters per second in the construction, you have no removal of oil, whereas if you go above, you get this pinching that we saw before. And as you increase again the speed, you have this you have less and less removal efficiency. So first, why we have this jump here? And one explanation that we're trying to find is with energy. So you have a double motion, which have an energy state 1, and a thin shell plus an oil drop. And to go from here to here, you need to create surface, so you need to create intershell energy. And this we call surface energy, ES. But we compare this surface energy to the energy that you give when you deform the drop. So when it's in the construction, when it's maximally deformed, we estimate the area of the double motion when it's maximally deformed, and we calculate the energy that you need to deform this drop. What was interesting to see is that if you're below 4 micron, when it doesn't detach, this deformation energy is not sufficient to overcome this splitting energy. Whereas if you go above 4 centimeters per second, you get this splitting, and that's where we see the removal of the oil. Okay, so there's a third. There's a third area that we're interested in, which is here. It's what happens if you increase the speed. Why do we reduce efficiency? And for that, we look at the shape the drop has before it enters the construction. So as I told you, it's already compressed. And you have the inner core here that has a center, and the outer double motion that has another center. And this difference of the center will give us the offset. And we measure this offset as a function of the speed. And this is what we find. So as you increase the speed, this offset is going to decrease. And that's consistent to the fact that the shaft thickness, the efficiency of the removal of the oil is reduced as you increase the speed. So what you want to get out of this is that the shape the drop has before it enters the construction is important for the oil removal. But so this device is interesting, but you have to put 1 drop per 1 drop, and those flow rate are quite low. So we went to upgrade another device, which we call the aspiration device. It's composed of a main channel with a lot of side channels, micro channels. And what the idea is that you put the double motion at the beginning of the channel and you get out thin shell. Maybe I can show you how it looks like when it's running. So here you have the double motion that arrive. As they go through this main channel, oil is being removed in the main channel, and they kind of jam together. And this jamming is very important for the removal of efficient removal of oil. And afterwards, in the second junction, they get removed. They get separated again. We can obtain with this technique thin shell, which have 250 nanometer shell thickness, but the throughput is 10 times higher than what we had with the construction device. But then, okay, so this is a device which has 30 channels, so 30 intersections. We can control this channel with the injection that we put, but also how fast we withdraw the oil from the microcapillaries. And to understand better, we try to do a modelization of this device. So what you need to understand first is that at each intersection, for example here intersection 1, intersection I, intersection N, intersection N, there is a certain flow rate and a certain pressure. And each of these channels have its own resistance. And what's cool with microfluidic is that since you're in laminar flow, you can modelize with the electric circuit. So for each point in the channel, you basically have a node. Here is the channel which were the micro channels, and here is the main channel. What you know is what you put in, Q in, and what you get out. This is the two parameters that you know. If you apply the node law in each of these points, each of these intersections, you obtain a matrix basically that link the pressure to what you observe, what you have at the beginning and what you have at the end. You can reverse this matrix and obtain the pressure profile. From this pressure profile, you can obtain the flow rate profile in the channel. So we make a lot of assumptions here. We make the assumption that the drop doesn't influence the resistance in the channel, etc. But so that's why we need to check a bit what we had. And here, to do so, we check the speed of the drop as they pass through the channel for different conditions. So here is the speed at each intersection. We have 30 intersection 1 and intersection 30, for example. But we start at different flow rates. Here 2000, here 1500, and here 1000 for the injection flow rate. And this techniques allows us to put the modelization on the graph, and what we it also helps adjusting a bit the parameter of our formula. So it seems to fit quite well. But I told you like we have 30 channels, but why 30? Why not like more? Why not less? And if we did some modelization for 10 lengths of 10 channel, 20 channel, up to 57. And this is the flow rate profile that we have for each of these. But maybe more interesting is the pressure profile that we have inside those channels. For n equal 10, so 10 channels, you have an end pressure which is around 10 megapascal, whereas for 20 you end up to 4 megapascal, but for all the other you're below 2 megapascal. And we were like, okay, can we still produce thin shell with those kind of devices? That's why we tested the shell thickness as a function of the number of channels that we have in our device. And we actually couldn't produce, as you can see here, thin shell from those 10 and 20 devices, whereas for 30 and more, we were able to produce sub-micron shell thickness. It seems that the pressure at the end of the channel plays a huge role if you can establish this jamming regime that I told you about. Okay, this is a nice modelization. I just want to show you quickly what we can do with this device. We put some double emission which have a huge distribution in terms of shell thickness. We had 5 to 18 micron in shell thickness. And we put them through the device, and we were able to obtain a shell thickness which is relatively homogeneous, around 270 nanometer. So that's cool, because you could imagine having another way of producing double emission, which is not necessarily microfluidics, and still obtaining thin shells. Then I want to talk to you about encapsulation, so I called my talk. But we have this model, we can control the shell thickness very thoroughly. And now our idea, and it's very early stage process, but our idea is to polymerize our double emission, which have different shell thickness, and form a solid state capsule, and then see if we could break them at different deformation rate. We first experiment, for example, here you see you have a double emission which is polymerized that goes through this channel. It doesn't get break, it's not broken. And if you look at this one, you have a smaller channel, a smaller constriction, and it breaks. So what would be cool to see is that if we have a different, we could tune basically the deformation that we have to apply a different shell thickness. So this is an opening for my talk. I want to conclude by saying that thin shell are cool because they are stable and they are low leakage. We see that we could remove the oil by mechanically removing the oil from the double emulsion. We could obtain higher throughput by using this kind of device. And next step is capsule breaking by using deformation. I want to thank my professor, Esther Amstadt, from the small lab, Gianluca Etienne, which is not here, but who helped me a lot, especially on the surfactant. And my master students, so Valentin, Baptiste, and Raphael, and overall the whole soft matter lab. Thank you very much for your attention, and I would be glad to take any questions.
Questions?
Maybe you say how do you measure the thickness of the gel?
No, I didn't say it. So we yeah, it's not possible because you're below you're 200, so you're below the limit, the detection limit. But we break the shell basically, and by volume conservation, we can get back the shell thickness. That's how we do it.
And in your double emulsion, did you check like coalescence mechanism or that kind of thing that might affect the stability of like foam in a room? Because you talked about the leakage stability, or I guess there are interactions between the different double emulsions.
Yeah, so the stability I've been of the emulsion. I didn't study, but some in the literature you can find some paper where they show like the coalescence of the drug, especially if the shell is very thick, like it makes the emulsion less stable. So there's a trend towards like thinner shell, more stability, because I also think that if you give more freedom for the inner drug to move, like you will have more potency for the inner shell to reach the outer shell, whereas like if you kind of fix it inside there.
Okay, so if you have the same shell, it's more stable. One droplet is more stable, but many droplets are more stable as well. Like, overall, you mean when it's all good when you decrease the shell thickness.
Yeah.
It depends what you want to do.
Okay, so I think we're going to go to the next speaker. Thank you. Okay, thank you.